So today I'm going to talk about online process mining. So I want to present you what this problem is and what it means to trying to solve this problem. I guess I will just skip this slide, right? So this is just the standard environment. We have our models, analytical models on the left-hand side, which are implemented in some information systems, which records event logs. And here the interaction between event logs and the models is where process mining sits. But this talk is about online process mining. So which are the peculiarities of online processing in general, not just process mining, but data mining as well? Well, the first point is that the input is different. So we don't have an event log anymore, but we have a stream of data. And in a general sense, the difference between a database management system and a data stream management system is that the relations that we are observing are not persistent. They are evolving, they are changing over time. At the same time, we cannot apply one-time queries to extract relationships that we're looking for, but instead we have to continuously update or continuously query the stream in order to get the information we need. This also means that we cannot have this random access anymore. We cannot say, okay, let's go to this process instance, to this event of this process instance, but instead we have just a sequential access. So we receive the data and we analyze and we continue. We receive, analyze, continue. And at the same time, more on the implementation side, we cannot really forecast how we're going to inspect the data, but instead we have to adapt to the conditions of the system. So let's say we want to represent an event stream, and here it's represented as sigma. We're going to just observe this stream of events. And in this case, each box represents an event, and the background color refers to the case ID. So you see here that different process executions are intertwined each other, right? Like you see that we see first an event referring to this brown case ID, then we see an event which is referring to another case ID, but we cannot really, so we have to split, to identify the different case IDs independently. So if we take the typical representation of an event log, we have it here on the left-hand side, right? So we're typically used to group events based on their case ID. So events that belong to the same process instance are typically grouped together. So let's say that the most important the field, let's say, in this case, is the case ID, which is used to group events. On the right-hand side, we have a snippet of an event stream. Here, the case ID is just a field like the others, an attribute like the others. And what is really important is the time. So the point is that here, the time is typically monotonically increasing. So we observe the event right now, and the next event will have a timestamp larger than the previous one. So as we said, we have to disentangle the different case IDs in order to reconstruct. And as we said, in the case of an event stream, the time is growing as we move on with the case ID. In contrary, typically in an event log, we just have the time that is increasing within the first process execution. Then when we move to the second process execution, we probably will have just, we restart with the time and we analyze the executions this way. So as you see, it's a rather different way of processing information. So more from a computer science point of view, we have some constraints that are typically identified in the literature. So the first is that we cannot store the entire stream. So the stream is assumed to be infinite. which means we cannot store it, which means we have to do some approximation. So in online process analysis, we're always talking about approximation. We can refine our approximation as much as we want, but we cannot guarantee perfect results. Unbounded backtracking is not feasible over stream. So since we cannot store our data, we cannot backtrack on this data, right? So the algorithms that are operating over data streams typically are said to do one pass over data. So as we said, we analyze the data and then we drop the data. So the point is that they have to scale linearly on the number of processed items, which means that for each event, if we take the process mining use case, for each event we have just constant time operations available. As we also said, we have fluctuating stream rates. So the system has to, from an implementation point of view, our stream has to cope with that as well. And since the stream is assumed to be infinite, that's the first point here, we have to assume that sooner or later our stream will change. So the source of information that is emitting our events sooner or later will be different. And for all of these characteristics, stream mining is a good tool to analyze what is now called big data. So here there are, you know, this big data now, it's this set of data which is characterized by different number of V's. So here there are 4 V's, but I guess now we're up to 7 probably V's, like there's also value and I don't remember what's the other one, but the point is that when we have this massive amount of information with specific characteristics, stream processing is a very good tool. Okay, when we think about process mining, we can group the techniques to do online process mining based on few aspects. So the first class of technique is called window-based models. The idea is to store a window containing recent events and then apply any offline approach that we have available to events collected in such window. That's very straightforward. Advantages are plenty. For example, we can apply any algorithm we have for offline scenarios in an online setting. Then the second family of technique is called problem reduction. Here the idea is to take a problem that is already known in, for example, the stream processing community and reduce a process mining problem to those other problems and apply solutions that have been already devised for well-known problems to the new setting. Then we have this family of approaches, which I think is also interesting. And the idea of this family of approaches is to shift as much as possible the computation from online processing to offline. So if you want, it's a kind of caching. The idea is to cache as much as possible the results that will be required during online at offline time. And then we may have some hybrid approaches that are kind of mixing the different aspects. Okay, so today I want to present to you some control flow discovery technique that we implemented a few years ago, and an online conformance checking technique. And the online control flow discovery technique I'm going to present are sliding window based, but that's not really a lot to present in that case, and problem reduction based, whereas the online conformance checking is this offline, is based on this offline computation idea. So, online control flow discovery. The online control flow discovery, as we said, let's say the setting of the problem is that we have our event stream represented here as this orange line with a lot of events that are emitted over time. Then in a certain point in time we decide to turn on our control flow discovery miner, and we get some result. And the idea is that our stream miner instance should keep this model updated with respect to the events that are coming in our channel. So the algorithm we implemented for this problem is called heuristics miner. This is a fairly old algorithm, but it's still widely used, especially in industry, at least in Italian industry. I guess that's because it's fairly simple and people can really understand what is going on under the hood. The most important metric of this algorithm is called dependency measure. And it's computed between two activities, and the idea is to analyze how many times two activities are occurring one directly after the other, minus the number of times that the other way around happens, divided by some normalization factor, okay? So the higher the value of this formula here, the more likely there's a functional dependency between A and B. Okay. So once we compute this dependency measure between all possible pairs of activity, then we can apply some threshold. Let's call it tau dependency. And the algorithm can then build a dependency graph considering all the connections that are that we can infer. However, if we have this situation here, so we have a dependency in between A and B, and we have a dependency between A and C as well, then we have some ambiguity that we want to solve. So is the relationship between B and C a XOR relationship, which means that after A, only B or C can occur, or is it a parallel, so an AND relationship? And to do that in heuristics miner, we have this AND measure, which basically computes if B and C are observed together. So B directly followed by C plus the other way around, divided by some normalization factor again. So we have a second threshold called, in this case, tau end. And if every time we have such ambiguity, like in this case, we compute our relationship, our end measure, and we apply this threshold. And if the value is above the threshold, then we classify this as an AND relationship. Otherwise, it's a XOR relationship. Okay. So the point here is that the most important data structure is the directory following matrix. So this matrix is basically a matrix with as many rows as activities in our event log and as many columns as activities in our event log. And each crossing indicates the number of times that A, for example, is directly followed by B. Okay, so we decided to leverage this algorithm for our online solution. And we identified three possible approaches. The first is a sliding window approach, which we used as baseline. So far there were no other online control flow discovery algorithms, so we wanted to measure our approaches against something. So we applied this sliding window approach. And then we decided to reduce our problem to another problem, which is called frequency counting, which is a well-known problem that we will see in a minute. So in total, we identified these three approaches, and the point is that the message is that all of them share the idea that recent observations are more important than old ones. So the recent behavior is more important than the old one. And if you think about the sliding window, then this is a bit of it's a very how to say sharp differentiation. So if so only the very recent events are important. After a certain threshold, which is our memory available, then there's no importance at all for those events. So for the sliding window approach, as we said, we can collect events for a while. So let's say this is our timeline. We can collect events for a while, and with a certain periodicity, we just apply standard offline approach on this event log. And then when we have new events that are coming in, we remove the old ones to make space for the new ones, and so on and so forth. The other two approaches, those based on lossy counting, start from a different idea. So the idea of these algorithms is to count how many times variables are observed in a stream. Okay? So we have these variables that we want to count, and this lossy counting algorithm also has as parameter the maximum approximation error that we are willing to accept in counting the frequencies of those variables. Then we have to compute, then it calculates this virtual bucket size, we will see in a minute, but the point here is that this is just computed out of the maximum approximation error. So this W is 1 over epsilon. And the idea of the current bucket, we will see in a minute what this is also computed based on the number of elements we observed so far divided by the size of the bucket, which again is parameter of the approximation error. And then this lossy counting algorithm keeps this data structure, which is a set of tuples where each element of the tuple is the variable. So let's say A, B, or C, it's the variable we're counting, the frequency of such variable that we observed so far, and the maximum error in the frequency of the variable that we have so far. We will see a few examples in a moment. So let's say this is our data stream, okay? This is our sequence of variables. We divide this stream into these virtual buckets using this representation here. So we count how many items we observed. We divided this number by our bucket size, and we have this notion of virtual buckets, okay? Then every time we observe a variable, we have to check if this variable is in our data structure D. So if it's contained in our data structure, then we can just update the frequency. So this second component frequency for the given variable. So let's say we observe B. If we have B in our data structure, then we can just increment the frequency. If B is not contained in our data structure, then we have to introduce a new tuple in our data structure with B as first component. The frequency is set to 1, because so far we observe only one element. And the maximum error, this delta here, is set to the number of the current bucket minus 1. And with an example in a minute, it will be absolutely clear. The point here is that every time a virtual bucket is over, we have to run this cleanup operation. So we have to remove elements that are old. And with old, we mean we have to remove all the tuples in our data structure D, such that their frequency plus the maximal error is less or equal to the current bucket. So let's see an example. This is our stream. This is the first bucket we are observing, so the bucket ID is 1. At the end of the processing of the first bucket, these are the elements we observed. So we observed 3 brown elements, 2 red ones, 1 blue, 1 green, and 1 purple. All these elements were not in our data structure, so when we introduced them, we needed to set the maximum error, the delta, as B current minus 1, you remember here. So their delta value is 0 for all of them. okay? So once we reach the end of the first virtual bucket, we have to remove the element which satisfies this inequality. Since delta is 0 for all of them, we just have to remove the element with frequency lower or equal to 1. So we have to remove these 3 elements here. So this is the situation at the beginning of the second bucket. Then we continue our counting, and we add these elements here because we already have them. And then we observe some greens block and some blue block. But now, since, as you see here at the beginning of the second bucket, there are no colors like these, their maximum error is 1, because it's the idea of the current bucket, which is 2 minus 1, which is 1. Then we remove, and we get, we do this, we perform our cleanup, and then we continue the procedure like that. So eventually, at the end of our stream, we have that these are the estimated frequencies, whereas these are the true frequencies. So as you see, this lossy counting is performing quite well, and authors also prove nice boundaries on the approximation errors. And specifically, we have that the approximation is always less or equal to the true frequency of the variables, which is always less or equal to the frequency plus the maximum error, okay? Which is also equal to the frequency plus, here this epsilon is the approximation error. So basically we can bound the correctness of our algorithm based on this parameter that we can set. So we can set the approximation error to 0, and then we have perfect, so correct counting.
Sorry, could you please repeat the previous slide? What is the left?
This one.
No,
this one.
These are beginning of.
This is the status of the memory at the beginning of this bucket here.
There are no lila.
No, there are none of them. Because here we didn't, because the only purple or
at the beginning of the bucket.
Sorry?
We are only looking at the beginning of it. Why there?
No, so the idea is that we are processing this stream one element after the other.
Yes.
So we go the first and the second and the third, so on and so forth.
We counted them in the bucket just in the usual way.
Yes. Yeah, right.
When you take the next.
Yes? So here, if once we reach the last event here, we have one purple element in here. But since we reached the end of the bucket, we have to perform the cleanup. And the cleanup consists in removing elements which satisfy this inequality. And the purple satisfy this inequality, so we have to remove it. And at the next step,
the smallest,
right,
the less frequent
right,
items.
right.
And then we have to remove the blue one.
So here we have to remove the blue one. This is right. So at the beginning of the next, we don't have the blue anymore.
Okay.
Yeah.
And how much do we save with this?
And I will show the results in a minute. I mean, this is not my algorithm. I'm just explaining how we reduce our problem to this algorithm. The point here is that here the parameter is not the memory, but the approximation error, this epsilon, okay? And I'm not going to present the second algorithm, which is called lossy counting with budget. But I just mentioned that the idea is exactly the same, except that the error, so now the parameter is the bucket size, and then the error can be computed, because as I showed in the first slide, all of them, all the measures of lossy counting are derived starting from this approximation error. And here the other way around is done. Okay, so how we reduce the problem? Well, we constructed three three data structures as those used by lossy counting. The first data structure basically contains the activity that we observed. So we have activity name, their frequency, and our maximum error. And then we have a second data structure, which is actually very important for us, because it is keeping for each, so we actually augmented the data structure a bit, but we kept the same rationale of the algorithm. But now we have, again, we still have the frequency and the maximum error, but now we have the case ID, so the process instance. So we're counting how many times we observe events referring to one process instance. And every time we observe an event, we update the second element, which contains the latest activity that we observed for that specific process instance. This data structure is actually functional to the third one, which is the number, which is a data structure which keeps the direct following relationships. Because if we have a process execution and we have the latest executed activity within a given process instance, if we observe a new element, then we know that between the previous, so the previous element and the current one, there's a direct following relationship. So the point here is that we can keep a data structure where the variables are actually the direct following relationships. Okay? So now we have this direct following matrix, which is now represented in different terms, but they are basically the same. So with a certain periodicity, we can just update our model by extracting out of our data structure the dependency measures, the end measures, and the XOR elements, and we can keep our model updated. Yeah, here there's actually one more point. So every time we're going to update the model, we're going to update just a local part of the model. But that's the implications of that we cannot ignore right now. We tested this approach against few data sets, artificial and real ones. So let's go to the performance. So here we have in this chart, we have a model-to-model similarity, where 1 means that we're able to discover the perfect model. 0 means that we're discovering just something that is not really related. On the x-axis, we have the number of elements we observed. So we simulated this stream for a few events. And these two vertical black bars indicate concept drift. So at this point in time, we decided to change the model that is generating the events with some different model. As you see here, so the yellow and the pink lines refer to the sliding window with two memory sizes, so with 300 event and 100 events. So you see that they're behaving quite bad. All others are referring to lossy counting with budget, with two memory configurations that are actually the same memory used by the sliding window, and the lossy counting with two different setup for the approximation error. And as you see, more or less all of them are able to achieve very good results. What is interesting is to see that after a concept drift, they drop their quality because they need some time to adapt. And actually, apparently, this second concept drift is a bit more tricky because it seems to take a bit more time before this adaptation is going on. And probably if we would have kept this going longer, probably they would have increased their their quality too. This is the memory usage. So here again on the x-axis we have the number of events, so it represents a bit our timeline. On the y-axis we have the number of elements that are stored. Let's start again with sliding window, with window 300 and 100. Those are, of course, flat, because they're keeping just that specific amount of elements into the memory. So except for the beginning, when they have to actually fill the memory, then these are flat. Then we have the lossy counting with budget. And since the maximum budget available is set to, again, 300 and 100, you see that they are fluctuating, but they're never increasing the threshold of 300 in this case and 100 in this other case. And the blue lines are referring to lossy counting, and as we said, there's no boundary on the memory for lossy counting because the parameter is just on the approximation error, and indeed you see that the memory is increasing over time. The time required to process each event, so we show that the time is constant, but with this experiment we show that indeed it's not just constant, but compared to sliding window, which are again these two lines, the two other approaches are twice as fast as the sliding window based approaches. Yes?
Question, how did you compare two models, model to model?
So for this one we used a metric we devised. It's basically it's based on the primitive relationships of the alpha algorithm. Mm-hmm. So we take the Petrinet, we extract the sets of allowed relationship and the set of forbidden relationships, and we compare two models in terms of the amount of shared behavior that is allowed and the amount of behavior that is forbidden. Yeah.
Does this relate to footprints?
Absolutely, yes. Absolutely. Yes. It's basically, it's a kind of footprint, so the comparison is based, it's the Jacquard similarity on the footprints. Yeah. Other questions? No. Okay. For the BPI challenge, since we don't have the reference model for this log, we just computed the precision. And as you see, I mean, it's a bit complicated to see the precision, but what we can see here is that the sliding window with a 1000 event is fluctuating quite a lot, which indicates that probably the results are not so stable. So the model is also not so good. And the average time required is again in order of magnitude faster for lossy counting and lossy counting with budget compared to sliding window. Okay, so conclusion for the control flow, online control flow discovery. We have these three techniques that we can use, and the techniques based on the reduction approach, so reducing the problem to another problem, these kind of techniques seem to work much better compared to just a memory-based, sliding window-based approach. Yes?
Are there different types of budget, or it's just...
What do you mean different types of budgets?
You can have budget and memory or time, etc. Some other resources.
So as far as I know, I'm aware of budget just in terms of memory consumption. Because like the time is fixed, so you just have constant time available per event. So, yeah. Okay, so now I want to talk to you about another online process mining technique, but this time is conformance checking. So we start from an event log and a model, so not an event log, but an event stream and a model, and we want to see to what extent the behavior observed in this event stream referred to the model. As I said, so the problem, this problem is I think is very relevant, because when you're analyzing the conformance checking, you're basically indicating that the executions in real world are deviating from the reference. But is it really useful to raise this alarm flag on a log which is referring to 6 months ago, for example? I'm not so sure. What would be really interesting is to have this real-time notification that some deviations are happening. And this way people can immediately drift back those executions to proper behavior. And right now the standard approaches for conformance checking are based on alignments. And these alignments are quite expensive to compute because they require a search in a huge space. This search is done using a star, for example, which has non-constant complexity. It depends on which heuristics you want to use, but it's not constant anyway. And additionally, an optimal alignment actually requires a complete trace, so that's even worse. So the general idea of the approach we implemented is to take our Petrinet and construct and move from this space to the transition system. For example, computing the reachability graph of the bounded Petrinet. Then the idea is to enrich somehow this transition system in order to include all the possible behavior. This is computationally, this is very expensive, but the point is that these first two steps are done offline. So we don't really care about the computational complexity up to this point. Then we compute the online conformance checking between our event stream, and not the original model, but this guy here that we call online conformance transition system. So how does OCTS look like? So the idea is that it has to represent all the possible executions of the activities of the process. Okay? So it's constructed starting from the transition system, which represent all the possible states that we can have in our model, but we have to extend it somehow. And the point here is that the transition system allows the replay just of the behavior that is contained in the original model. But since we want to allow deviations to occur as well, we have to include deviations in there. Still, we have to keep some properties in this enriched OCTS. In particular, it has to be a deterministic transition system, which means that for each state we want just one transition exiting with a given label. This way we can have this constant time complexity in the selection of which transition to keep. And from each state we want to have one outgoing transition labeled with all with the whole alphabet of the starting model. And then we attach to each transition a certain cost. So transitions allowed by the model have cost 0. Transitions that are not allowed by the model have cost larger than 0. Therefore, the sum of the costs, if we do the replay of any trace on top of such OCTS, then the sum of the costs for conformant traces is guaranteed to be 0. So if we replay a trace that is in line with the reference model, cost is 0. Otherwise, if the execution is non-conformant, then we have a cost larger than 0. This cost larger than 0 is not actually the optimal cost as in the offline alignment, but it's larger than 0. So these two properties here indicate that this structure is okay for being used in online setting, and these two properties down here mean that it's a good data structure for conformance checking, because these two properties are precisely what we want to to achieve. So the challenge here is how to pre-compute offline all of these deviations. So let's start from a certain Petrinet, but we're not really interested into the Petrinet. We're interested in the transition system that we can extract out of this Petrinet. Let's say we're now in state 1. So we're here, and we observe activity C. What should we do now? So from state 1, we have just one transition outgoing, and it's labeled B. So we have two options. The first is to ignore C. So we can say, okay, we received this event, but for some reason this event was wrong. So we ignored it. We ignored that. Or we can decide to replay this execution on top of our model, because actually our model allows C's to be executed. But if we decide to replay C, then we can go to state number 3 here, or to state number 5, which is here. So it means to follow this transition here or this other transition. Okay? So for those of you who are into alignments and conformance checking, ignoring C means to perform a log move. Replaying a C means to do some model moves followed by a synchronous move. So we decide to synchronize on C, but in order to synchronize on C, we have to do some model moves before. The problem here, of course, is that we have just partial information, so we don't know the context, so we have to assume something. So before presenting how to do, I want to briefly tell you what Reagent Theory is. Very briefly, it's so let's say we have our transition system and a subset of the states called S prime, and we have a transition labeled called sigma. Okay? Then we can define 3 properties. The first is called no cross, enter, and exit. And if we take this small transition system down here, and as S prime we select state number 2, 5, and 4, then you can probably already imagine what these properties are referring to. So if we take the no cross property, then this subset has this no cross property for activities for labels B and for label C. Then we have the enter property for label A, because we have a transition entering this subset label A up here, and actually another label the same down there. And we have the property exit for a transition label D, which is this one. Okay? So, yes?
Is it minimal region?
No, I'm just presenting the properties. Now I'm coming to the regions.
Sorry.
Yes?
The previous slide. So 3 enters 4.
3 is connected to 4 with a transition labeled A.
Oh, so it enters but why 2, 4, 5?
Because so we're interested in the subset of states S prime. And this subset is made of state number 2, 4, and 5.
Okay. No cross. And why B no cross with 2, 4, 5?
Because I'm coming now. So if we consider all of the transitions, all the labels of the transitions in our transition system, then if we have 2 properties, it means that S prime is a region. So if we have that for a given sigma, we have that we have a transition entering, but the same transition is not crossing, and the same transition is also not exiting, or if it is exiting, but it's not crossing and not entering, then this S prime is a region. So if we take again this example, and our alphabet is A, B, C, D, then we can check if this subset S prime is indeed a region. So we start with the first label, A, and in this case both are fulfilled. And in particular we have that A is entering here and there, but it's not crossing and it's not exiting. B is also fulfilled because B is not crossing, so that's fine. C is the same, it's in here, it's not crossing, it's fine.
Sorry, it's not obvious. Enter actually what is crossing. B and C are inside.
It means that you have a transition connecting states which belong to this subset S prime, but just internally. So it's just connecting states within S prime.
And
B is connecting 2 and 5.
So it's crossing.
No, it's not crossing. It's no cross. So it's not crossing the boundaries.
No crossing.
It's, so the terminology maybe.
So no crossing means exiting or entering.
Exactly. Yeah. So the point here is that all of these properties, so these two properties are fulfilled for all the labels in our alphabet. So this is indeed a region. So intuitively the idea is that we have a region if the transition labels share the same entering or exiting behavior. So if we have transitions labeled A and these A's are entering, then we know that these transitions are just entering. Okay. So now back to the construction of our OCTS. So from a process point of view, the point is that regions, if we have transitions within a region, we're not really changing the status of our system. We are remaining within the behavior of that specific region. So if we take a certain state and we have to execute an activity C, we select a log move, which means we discard the event from the stream. If within any of the region of the current state, we have a transition labeled C. So let's see an example. Let's say we are in state number 3 and we want to execute C. Okay? So if we highlight all the regions of the transition system, these are the regions. And actually we do have one region which fulfills this property. So we have a region, so we are in state 3 and 3 is part of a region which contains C. So then we're just going to add a self loop, which would imply that if from state 3 we observe a C, we're remaining in the same state. And as I said, the rationale here is that this C is not really affecting the status of the system. And that's because we have this transition here. Okay. If this is not the case, then we have to perform this sequence of model moves followed by a synchronous move. So to add this new transition, so let's take now this other example. We're in state 1 and we want to execute activity C. So synchronous move. So we have to first select the candidates for synchronous move. Synchronous moves candidates are state number 3 and 5 because they are sharing this incoming transition label which is C. But then we have to select which of these two to actually go. And the idea we proposed is to to have some representation of these states based on the history of the traces that are leading to state number 3 and number 5, and to the current state, and pick the state that share the most similar history. Once we decide which one to consider, then we can add the transition. So let's see how we compute this similarity. So I will just go very quickly. The idea is that we just consider the path from the beginning, from the initial state, down to the current activity, to the first candidate activity, and the shortest path to the other candidate activity. And then we compute the cosine similarity. I'm just skipping this part because it's probably not relevant, but the point is that we just pick the candidate which share most of the history with the current state. In this case, it's state number 3, so we can introduce this new edge which goes from state number 1 to state number 3. Okay, of course the construction of this transition system is not unique. So we can think of this OCTS as this way of computing the online conformance, but the way we can build this transition system is not unique, and this is just a suggestion which is basically so our idea is to mimic the concepts that are in offline conformance checking of synchronous move, model move, and log move. And we can think about other ways of constructing the OCTS. For example, we can think about a no deviation allowed way of constructing, which is like that. So we start from our transition system, and every time we observe a non-compliant label, we can just go to this sync place, which is collecting all deviations. Okay, then the online conformance is actually fairly simple in the sense that it is just reading the events from the stream, picking the current state of the execution, and then continue and perform the replay from this state to the next one, following the observed event, and summing up the costs. Okay, actually, as the previous algorithm, this is also implemented into Prom plugin. Prom is this open source platform for process mining. So you can first create your OCTS, and then you can do the replay with this dashboard, where you have on the right-hand side some general statistics, like the number of errors over time. And on the left-hand side, you have the list of executions, which are color-coded based on the cost. So how much they are deviating from the reference behavior. And if you double-click on one, you can actually see the reference transition system, and you can highlight the specific deviation. This can be useful to kind of investigate why a given deviation occurred. Okay, we tested against this process model here, which is, I think, a good test because it's very big. And we all know that when we talk about transition systems like reachability graph, if we have big models with a lot of parallelism, then these transition systems are huge. That's why we picked this fairly big model. And then we simulated this model for 1 hour of world clock, so 1 real hour. And basically, we set the generation to 65 events per second. And as you see here, we were absolutely able to keep the pace of the generation. And consider that here, both the generation and the conformance was run on the same computer. So there was a bit of overhead. And, but yeah, I mean, from a theoretical point of view, Each event is again requires just constant time, but even this prototypical implementation was able to keep the pace. Okay, so conclusion of this is that this approach is one of, so in the taxonomy I presented in the beginning, here the idea is to shift the computation, the complexity of the computation from online to offline. That's very useful, especially if we have such time-consuming operations to do. But the advantage is that then we can indeed do conformance checking based on that. And actually, I'm working on this topic right now. So we're planning to extend this approach to see if we're able to, for example, exploit contextual information. Because right now, contextual information is basically ignored, except for this similarity, but it's still a bit of a challenge. Okay, so. Yes.
Well, you told about the transition system, and could you explain why we should use just transition system, not a Petrinet?
Yes.
Why?
So the advantage of it's to keep this computational complexity to a constant level. So if we are able to generate a transition system such that in a given state we have to check just a constant number of outgoing transitions, and specifically this constant will be the same as the number of different labels in the transitions of the Petrinet. So we have one transition exiting for each label. Then we can just scan this list of transitions and pick the one that is referring to the event we observed. That's it. If you want to do the token game on a Petrinet, then you may have tokens distributed around the Petrinet, and it may not be trivial how to move the tokens around. So that's the advantage. So to conclude, I think online process mining is a very nice topic, especially because it has very nice challenges for a computer scientist. So it's a very nice topic. But outside of academia, I think it's also super useful for real companies, especially if you think about this online conformance checking. I think it's incredibly useful for them to know immediately which executions are deviating from the reference and why. And some initial work, as I presented, has been done in particular on the control flow discovery. So I applied the same principle that I presented today for the heuristics miner to the declarative domain as well. So there is a declare online control flow discovery algorithm available, and to conformance checking. But yeah, best is yet to come. So that's it. So thanks for being here, even though it's late. And if there are, yes.
Show the slide with all CTS.
Yes.
Production generation.
Yeah. So, which one? The very first one, or let's take the first one and then we see. Okay.
So the result is in the right lower corner, yeah?
This is the OCTS. Yes. The idea here is that solid edges are the same as in here. So
this is above, you have the real model.
Here, this is the transition system that you can extract out of this Petrinet. So this Petrinet allows for the behavior that is described in here. So they're basically representing the same thing in different ways. But this is basically expliciting all the possible states that this process can be on. So here we have all possible states, but not all, and we have all allowed transitions from one state to another one. But as I said, we want also transitions, and here depicted as dotted lines. The dotted line here represent transitions that are not expected here, but may be possible. Although they would imply that there's a deviation from the reference behavior. So here the dotted transitions are going to have cost larger than 0. Solid transitions will have cost equal to 0.
Okay, I can understand that transitive edges appear, but how the reverse edges appear, which are
like this one.
Yeah.
So the point here is that if you are in state number 6, you want to have one outgoing transition for each label in your Petrinet. And one label is A. But if you are in state 6, you have to go somewhere with, you must have a transition labeled A. So where should this transition go? Here the idea is to go to the very beginning, since there is this incoming transition to state number 2. So state number 2 somehow is the state that is reached after executing A. So the rationale here is to say you execute A.
I understand
Okay.
with the 6, but then with the 5 is not
With-
clear, because with 5 you have to go to 6, not back.
With A? No. With-
from state 5 according to your...
So if you are in state 5 and you observe an A,
if you observe...
where should you go? Again, you can apply the same principle, and that's why you have this back edge here, labeled A.
Maybe I didn't understand the basics. You say that A can appear after 5, but it is not allowed by the model above.
Exactly.
But you still have this data, or what?
You may observe that. So you cannot assume that it will never happen. So you have to say, maybe this will happen. So if this happen, then this is the behavior that we are suggesting.
What is the status of the model above? It doesn't describe all possible transitions.
This one?
Yeah.
This describes only the transitions that are allowed by the model. But so maybe it's a good idea to step back. If we have a reference model, it's not, we may have executions that are deviating from this model. This is the basic idea. Because if you have an information system which implements this process, you typically want to have some flexibility.
So this
So
normative model. Yeah.
This is a normative model,
Oh,
precisely,
Yeah.
precisely, precisely. Yes?
Would you say, sorry, about complexity
Complexity of what? Of constructing that? I didn't compute the complexity, but I'm sure it's quite huge. But I didn't compute. But the point is that for this work, the complexity here is not really important because it's offline pre-processing. So it is acceptable to have very high complexity, but it's high indeed. Yes, there was a question on that? Yeah.
Yes, as far as I understand, this is a sort of monitoring system to indicate any deviations in the strictly algorithmized processes. Let's say RPA. Let's say that you implement a robotized process in an organization, and should anything goes wrong, this approach would let you know when and how exactly. Am I right?
So the point here is that
let me be more simple. Could you give me an example of practical usage of these model?
So I'm not sure if you're asking me about the usage of conformance checking or the usage of online conformance checking. So in online, the advantage of online with respect to offline is being able to know immediately about the deviation, and so there's time for who's in charge of the execution of the process to realize that there's such deviation, and maybe they can drift back to the normative behavior, to the reference behavior. Yeah.
But by the way, your approach suits only strictly algorithmized processes.
Sorry, only?
Let's imagine that a human being
Mm-hmm.
performs any business process.
Yes.
In a system. Yeah, just be simple. And you cannot predict all the actions that human could take during this process. Would your system somehow reassure that these deviations are against the normal process, or they could be just habits of this person? Unless you have the strictly written scenario for the process, how could you understand? You cannot, right?
So you're right. So the starting point is a process.
Mm-hmm.
So we must have a process specification.
Yeah.
We must have a process. And then we are indeed considering only the activities that are in such process. If, let's say, we have here activity A, B, C, D, but we observe activity K, of course we don't know what to do with K, if this was the question, and if this is answering.
Does this approach suit to indicating the deviations in those situations when we have some non-critical deviations? I mean, let's imagine that someone performing an action and then stops in the middle of the process and goes for lunch.
Yep.
Right? Would your system indicate that there is a strict deviation and we need to put our efforts to manage this?
No, this process, with this work would not be able to do that, because here the deviations, let's call them deviations, are just in the control flow, which means that a deviation is when we're performing activities not in the order that is prescribed by the model. So if you just do what is called a partial trace, so you start your execution and then you suddenly stop, we cannot know if this is a deviation. And that's because we are analyzing the events in real time. So we receive this event, but we don't know if the event afterward, that process execution is going to continue or not. Thanks for the question. Yes?
I have a comment. I think that maybe we are able to construct a general model from the very beginning of a user behavior, for instance. Not only observed, but just to generalize here from the very beginning, and then maybe we will see some kind of deviations. Then our system was used by some kind of a bot or something like this. So
yes.
It's possible. It's up to us on the first step to construct a more general model.
Yes.
And so I have the following question. Since we use Reagent Theory here,
yes.
We already have
yes, this is right.
model, and here we have places as regions.
Absolutely.
So we
it's very easy to compute the regions down here because we have the places.
We already have them.
You're absolutely right. You're absolutely right. Yes.
Taking into account that it's a time-consuming algorithm.
Yeah. And actually, just to relate your observation to what was previously mentioned, there are some initial works on process mining for intrusion detection. So if you think about your system, you can probably specify what is the reference behavior of your software, for example. Okay, so let's say you have a set of APIs that you provide to the developers, and you can write which way you expect those APIs to be used. And then you can apply this machinery in here, and you can turn on the online conformance checking to see if these API are used indeed as you design in the beginning, or if someone is just trying to abuse of the system by doing weird calls or something like that. So if your cost for such execution is increasing too much, then you can say, okay, you are now banned for, I don't know. Yeah.
Can you update your model with weights on the arcs or some kind?
Sorry, if.
Could you update? Can you update your model by putting weights on the arcs?
Yeah, absolutely. This is what we do. So arcs with solid arcs have weight 0. 0 is what, so this weight is what I call cost, but that's exactly what you refer to. Arcs that are dashed have weight larger than 0.
You just didn't put it.
I didn't roll them here because it would have been a mess otherwise, but yeah.
Because it has probabilistic interpretation, the weights.
If you want to go for you can probably assign a probabilistic interpretation to the weights as well, but then I would say that the solid ones should weight 1 because they're kind of certain, and these others, the dashed one, should have weights lower than 1, between 0 and 1 probably, and then you can keep multiplying, not summing up, but just multiplying those weights, and you have the probability of that execution to be part of the reference model. So thanks for the question. Other questions or comments?
Small question.
Yes.
Am I right that this is defined is known as totally defined final state machine? No?
Could be. I think so.
Complete finite state machine.
No. No more question? Okay. So thanks and.
Thank you.